Hi there, welcome back. Welcome back to video number 3, and this time I promise you it's the last one on the series. And this is the last one of the restoration of this easy project, as I mistakenly described it in the beginning. This time I know it's the last one because I'm filming this at the end. I'm not being stupid again. I ended the last video with the few surprises that I had found, that I'd had, and I decided to do them and then at the end do a summary as part of the introduction. In this video there's quite a bit of doing and quite a lot of testing, so stick through to the end and I'll show you what happens here. We'll do the testing, the power section, the audio section, the playback and record functions. This will all be done on the scope and instruments, but the one thing I wanted to try out, and I'll show you this on this video, is the frequency response curves that those two filters give you, the 7.5 inches per second and the 15 inches per second settings. Different response curves, as is to be expected. So we'll see that at the end of this video, and enjoy it. I'll start by showing you what some serious cleaning can do. This faceplate is in incredibly good condition, and all it took was some cleaning. Now you've got to be careful you don't clean off the labels. So this was done with dishwasher liquid and just basically the mildest soap you can get and some water. Carefully cleaned up. The knobs were polished because these were a little bit tattered, and they've now come out beautifully. Obviously these were cleaned up, that was cleaned up. There was a nut missing here, so that was put on. Then I dismantled the meter because I didn't really want to do that, but it's such a great looking meter that I wanted to get it really, really spotless. And that's the result. I mean, this thing came out really nicely. It just, there are 3 screws at the back. You take those off and then you remove the meter, the whole meter, and you're left with the glass. So that came off. All the glass is cleaned up. On the inside there were some spots, so that got cleaned up, and then you just polish it up and put it back in. Nothing was changed in the meter. You've got to be very careful you don't damage the movement or anything else. And so the result is it looks like a brand new meter with a difference. It's bloody beautiful. I love this thing. And the knobs, well, they had, this is sort of a Bakelite knob. So what I did was, because the damage was only on the external surface, I actually got some wet and dry sandpaper and just gently, very, very fine, I think it's like 1200 or something grit, and just polish this. I didn't get a shine back. I don't really want to. I think it looks great like this, but they now look totally uniform. Obviously the rest got cleaned up, and we've got ourselves our knobs. And everything is hunky-dory. So that was the cleaning of the faceplate. I've also done some cleaning on the chassis itself. The chassis also cleaned up pretty well. There are certain things you've got to be careful with. I mean, things like that. This is actually in the paint. I mean, you do the best you can. You could go crazy and polish it, but then you'd wipe out all the labeling on there. I don't want to do that. This part here cleaned up pretty well. Again, very, very mild soap and water. And these things got polished, so everything is looking really, really good. This is what the cable looked like, and as you can see, it's completely brittle. This was going into the plug, and it's just basically it's just breaking apart. So I put in a 3-wire cord. Actually, I put in this. I've put the original plug back, which has only got 2. And so what I have is I've got the earth one just basically tied up on the inside there and cut off at the plug. If I want to change it to make the chassis mains earthed, I can then just change the plug and we'll decide how to go from there. It all depends on what sort of noise we get. So that's already done. So this thing is ready to power up. And the first thing I'm going to do is I'm going to set the heater voltages. Before I do that, I want to show you what the variable resistor is they've got in that line, in the heater voltage line, the one that says adjust for 12.6 volts. What they've got is from the rectified voltage, from the selenium rectifier they had in there, it would go through this and then it would go through to the filter cap. And this thing is a variable resistor which you basically unscrew down there and shift up or down on this wire wound, well, on this winding. it's not at all precise. And as you can see, it's pretty close to the end there, pretty close to the maximum resistance has already been used. So I'm going to leave that one as is, and I'm going to adjust the resistance that I need, the extra resistance I need to add into the little board that I've got in there. I'm going to adjust that and leave this one as is. In fact, I think I might just pull this one up a little bit so we get a little bit of leeway, but then I'll be able to adjust the resistor for that little board that I've got to get 12.6 volts. And to do that, we've had to do something else. As you may recall from the schematic, the heater voltage, the 12.6 volts heater supply, is for these two tubes, the 12AU7, 12AX7. Now, each of them, according to the data sheets, draws about 150 milliamps on the 12 volt setting. If you don't know, you can run these on 6.3, in which case pin 9 becomes a common ground. But this thing is wired pin 4 to 5, so it expects 12.6 volts, which is what we're trying to give it. And to see what current or what voltage we're going to get, we need to actually have a load on here, because that variable resistor drops voltage depending on the current. So basically, you put the tubes in. The supply won't work because I've got the rectifier valve disconnected, not in circuit. So we're not too worried about the B plus right now. However, the heater supply will work, should work. And another supply that will work is actually the heater supply for the rectifier valve, which is also used in something else. And that is, it's used to light up the dial lamp inside this meter. So I've wired that in, and by switching it on under some protection, we'll be able to determine what resistor we want for the heater voltages to get 12.6 volts. We'll also see if that thing works. So let me show you how I'm going to set that up. So first of all, I've got a new toy to show you. This guy, this is a Variac. If you remember, I mentioned in the Breisgau series that I was wanting to get one of these, and the problem was shipping because they're quite heavy. Well, one of you went beyond, way beyond the call of duty and sent me one. I want to thank Heinz for this. He went to extreme lengths to get this to me because some suppliers weren't shipping this device to Madeira. I think he actually ordered it twice and it was returned. And then finally he ordered it to himself in Austria and then sent it over to me. So this thing has arrived. It's a 0 to 300 volts. It's a 220 volt or 240 volt input, and the output goes up to 300 volts. And it's fantastic. I love it. So what I've done is I've got this coming in from the mains. The dim bulb tester is connected to that. So I'm putting it on limit just in case. I'm putting one light bulb. These are off. That's off at the moment, so I was switching it on there. I can switch this on here. Now, if you recall, this thing is a 120 volt device, and I do have the owner's transformer here, but I'm going to use that because I want to dial it up slowly. And as you can see, we can go up pretty slowly. And what I'm going to do is I'll just leave it off, and then I'll go up to 120 volts on there. This thing will be protecting just in case there's a complete short in the circuit. I don't want to risk it. And then I'll be able to just bypass that, and we'll be seeing the full mains voltage. Full main voltage meaning 120 volts or 115. I'm going to go up to as far as 120 because we do go as far as 240 over here. So in 240, this thing will see 120, and I want to get 12.6 volts for those heaters. So let me show you what I'm trying to do here. What I've got there is I've soldered two wires to where the resistor will go. This is just so that I can get contacts for the croc clips. And I've got these two crocodile leads connected across those two wires. Remember, if I short them, I basically have no restriction after the diodes, after the rectifier. And if I want, I then put a resistor in place. I'm measuring the voltage, the heater voltage at the filter cap, the 1000 microfarad filter cap that's down there. And now I've got these leads coming out here, ready to receive resistor. I think I've got everything ready now. Here are the two wires that will see a resistor across it. At the moment there is none, therefore there'll be no current. So what I'm going to do is I'm just going to short it. So zero resistor. In other words, the selenium rectifier has been directly replaced by the silicon rectifier. And we'll see what we get as we turn up the voltage there. I'm not sure what we're going to get. I'm going to put this on. And let's start giving it some voltage. Put this down, switch it on. At 0 volts, that thing won't come on. It needs some voltage first. So let's see what happens. I've got a limit on. I've got one light bulb. Switch that on there and see what we get. I'm going to put it up to about, let's put it up to about 50 volts. 2 volts over there. Aha! That's come on. That's definitely come on. Watch. So the dial lamp is on. The that other winding that just supplies the dial lamp and the rectifier tube's heaters is working. Not sure what voltage we're getting there, but this thing's definitely too low. And it's at 50 volts, so I'm going to go up a bit more. Put it up to 80 volts approximately. 6.4. Because this thing requires a bit more voltage, it starts at 80. The readings here are a bit iffy, but that's the voltage it's getting. And of course there is a limiter on here, so I'm going to leave the limit on and I'm just going to keep putting this up. 100 volts, 8.2. Okay, I know there's no short, so I'm going to bypass that. Wrong switch. That one. 10.8. We're still at 100 volts. 110. That's already going too high. So if I put that at 120, which is what I want to test it to, this thing's going to go way up. So that's not good. Okay. Switch that off. And now I'm going to put a 10 ohm resistor in here. 10 ohm resistor. And we'll switch that on again. About 10 volts. I'm going to go up to 120 over here. Okay, 120 over there. No limit. And it's 11.4. So that's not enough. I need a bit more. And the way to get a bit more is to put another resistor in parallel with that guy. If you recall, those boards allow for 3 resistors. So I'm going to take another one here and I'm just going to parallel them. So instead of 10 ohms, we'll have 5 ohms and we'll watch that guy there. .5, 12.6. 12.64. That's pretty good. 12.65. Now remember, this is at 120 volts. That's assuming my mains is sort of 240. It's usually about 235. So if I come down to 117 here, I get my 12.3, which is close enough. And if I go down to 115, I don't recall seeing that come below 230 volts. So that'll give us 115. That's 12 volts. That's perfectly fine for the heaters. So what I'm going to do now, switch it off, and I'm going to solder these 2 resistors in parallel onto that board, and our heaters will be fine. Let me get on with that. And there we are. 2 resistors in place. If you notice, the central one, I've actually drilled through it to actually bolt it to the chassis with a spacer. I knew I wasn't going to need 3, so I've got 2 2-watt resistors. That's 4 watts. It's dropping about, I don't know, 2-3 volts, not more than that. Probably less than that. So I've got no problem with power. So my heater supply is done. Right, I'm ready to do a proper power up now. I've put in all the tubes. I've got the 12AX7, 12AU7, and I've also got the rectifier tube in there. And I put in a new rectifier tube because the owner told me there was something wrong with the other one, so I'm not even trying the other one. And I've got the little brothers measuring the B+ straight out of the rectifier to the first filter cap, so that should be the highest voltage. And then I've got that guy measuring B2+, which is after the 2K resistor. That's the one that's actually going to the main supply to the anodes of the tubes. So I've got the switch on at the front there. We know the heater voltage is 12.6 or thereabouts. So I'm going to switch it on. The variac is at the moment on 100 volts. I've got the limit on here, 2 light bulbs. It's on limit. I'm going to hit it. I don't want to take any chances. That would help if I put it on DC. Yep. Okay, so that is higher than that one as expected. We're not too worried about the amounts right now. I just don't want to see incredibly low voltages, which would mean we've got some sort of short. But that seems about right. Now I'm going to take this up. It's drawing 150 milliamps. I'm going to take this up to 110. Everything still seems okay, but I do need to take off the limit. So let me get rid of the limit. So I'm bypassing the limit. Let's let that stabilize for a while. 30 volts difference. That's about 15 milliamps. That's not bad. That's across 2K resistor. Taking this up to 115. So we've got the full voltage on there now. And we have 304, 272. Let's drop to a bit, 115. Okay. Now, according to the schematic, I'm not too worried about the absolute values. I want to see what current they expect on here. They say 354 and 321. So we've got, 33 volts difference on 2K. It's about 15 milliamps. We've got 32 volts difference on here as well. Now, I have tested this before, I've got to tell you, and I was a little surprised that this thing only went to about 307. According to the schematic, it says 354, but I tested something else. It does say that the winding, that main secondary winding, is 300 volts. And what I measured on here, when I did measure the AC, is I got 270 volts. So the transformer is not producing 300. It's producing about 270, which that accounts for that voltage difference. So I think the schematic is actually wrong. Or they measured in a strange circumstance where there was no current draw, which is a bit strange. But nevertheless, we have 78, 22, 30 something milliamps. So we've got 15 milliamps being drawn by the 4 triodes of the 2 tubes, which is what it says, according to the schematic, that's how much current's being drawn. So I think we've got this thing working. What I'm going to do next is I'm going to provide a signal from the signal generator into the, what will it be, into the recorder input. Okay, and then we'll be measuring the output here at the 600 ohm output on the scope and see what we've got. Because according to this, the power supply is working fine. That's sort of creeping up, but then that also creeps up, which means that everything is just warming up and stabilizing, which is good. It's giving us the right signals, or the right message anyway. We'll see about the signals in a minute. Let me set up this so we can get a signal going through here. I'm going to make sure that I get this right so I don't create any ground loops and short out oscilloscopes or anything stupid like that, which can happen. Right, let me get on with it. Right, I think I've got everything set up. I've got the signal coming in at 10 millivolts, going into the input of the recorder. It's on playback. I've got the level very low because I don't know how much gain this thing's got. The input signal is 10 millivolts RMS. Again, I don't know how much gain it's got, so I'm not sure what I'm supposed to put it at. So now I'm going to switch it on. We'll watch the scope. See if there's any action. Oh yeah, okay. There it comes. Nice, 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 nice. A bit of wobble because I don't have the shields on the tubes, which is fine. And now what have we got? We've got, let's see, what is this at? It's fairly low still. I've got the end terminated here with 600 ohms. Okay, if I take that off, that'll jump up. I might do that at the end of this test. And I've got the two the two outputs of that connector. One is pin 2 of that XLR is the yellow, and pin 3 is the purple. And I was a little bit surprised by this. Yeah, I for some reason I was expecting a fully balanced signal. This is not a fully balanced signal. This is actually a differential signal. Now, I'm not sure that if I'm making stuff up or not. So if I am, please tell me, and put that in the comments. I think what happens here is, why do you take this signal and pass it through a balanced attenuator? First of all, they probably didn't do that. I think this was done by that attenuator that was added on there. Whoever did this mistakenly considered that a balanced signal, and it's not. It's referenced to ground. The transformer has got the secondary, one leg of the secondary connected to ground, so it's not a balanced signal. So you should actually have used, or they should actually have used, a single-ended T-pad attenuator, and not, or H-pad. It's not an H-pad if it's single-ended, but then never mind. They should have used a single-ended attenuator. Now, why would you use, what advantage could you gain from using this system? The only one I can think of is your signal at the end, when you take the differential signal, is going to be much smaller than either of the two, or than the original signal, because your purple trace, as you can see over there on the screen, is, do I have these at the same level? Yes, I think I do. Yep, 500 millivolts per division each. You're actually going to get a fairly small signal because one is subtracting from the other in a differential, in a balanced input, if it meets a balanced input on whatever this is going to. The only advantage I can think of is if you're going to run a long cable, then what will happen is both lines will pick up the same common mode noise. That's why it's called common mode noise. And therefore your common mode noise rejection will actually still work, although this is not a balanced signal. I think that makes sense. If it doesn't, as I said, please tell me. The point is, we've got this thing working. And let's see how far this goes up. Let's do that. So it's at 2 volts per division, and it's going to start peaking already. Okay. So what do we have there really? We've got is this thing in here properly? Yeah, it is terminated. Is this clipping at the bottom because of the input or because of the output? I'll put it 5 millivolts RMS and increase the gain. It's actually clipping because of the output, so that really is there. Our useful signal, and that is, what is this? This is at 500 millivolts per division, so it's about 3 volts peak to peak on the single-ended side. If you take the two apart, you've got about 1 volt peak to peak, which probably isn't that great. Well, it's fine for a line level. I'm not sure what it's supposed to be, but again, this thing has been tampered with on the output, and maybe that wasn't such a good idea, but we can always reverse that. That's the beauty of this. The point is, it's working. It's working. Now let me just switch that channel off. Let's see if we've got a monitor out. In other words, if we've got a signal there. Yes, that is on that headphone monitor out. And again, adjustable. Okay, all right. Obviously this 1.5 and or 7.5 and 15 does nothing because that's for the record. And with the record, we can actually test that as well. We can put the signal into the microphone and we can monitor the record out. Let me just change that and get back to you. Right, this is now set up in the following manner. I've got the signal generator coming in 5 millivolts RMS, coming into the hot input of the microphone. I'm not going to do a balanced input here because I don't want to short the scope ground and generator grounds. So I'll just use the hot, and so that's referenced to ground. And then what I have is I'm monitoring the hot channel or the output of the recorder. Remember, single-ended again, and we'll see what we get. I've got this on the switches now on record instead of playback. This is still fairly low, so let me switch it on and I'll bypass it. It's 5 millivolts input, very low. Supply is behaving itself. Oh, we got something. Yep, there we go. There we go. This is our record output now. That's the microphone signal being amplified. Let's see where this goes to. Actually goes higher before clipping, which is a bit odd. 10. This output is now, oh, no, that's 500 millivolts per division. Okay. Yeah, okay. This thing's going higher before it clips, and it makes sense because if you recall, that output has actually got, I'm increasing the level now, it's on 30 millivolts. And if you recall, that scope, that output there, when we were measuring the output, actually had 12 dB of attenuation. So that would make quite a difference to the maximum usable level. I've got a feeling when we connect this thing to the transport, we'll probably, or when we get this thing working properly in the system, we'll probably have to remove that attenuator. I'm not sure. But yeah, that's working fine. That's working just great. That's brilliant. Brilliant, brilliant, brilliant. Okay. Ha! I like it. I like it. Okay. Let's move on. There's one more test I want to do, and that is to plot the response curve for those two speed settings on the tape. And because that applies to record, obviously, I want to set this up so that I can send a signal in, alter the frequency, and see what we get on the output. The output being the connection that goes to the recorder. So I've got the signal coming in on the microphone input, just like before, and the output's going to the scope at the moment, and it's also being monitored by this multimeter here on AC volts. And if I just up that, we get our voltage and our frequency. It's 1 kilohertz sine wave. That's fine. And I can also see it on the scope over there. No mystery. Okay, so what I want to do before I start trying to plot that, in other words, before I alter the frequency and see what response I get, I want to know what the output impedance of this is. I want to know what impedance it's expecting, and I don't know what the input impedance is of the transport. So when you are sending the signal from here to the recorder, it sees an input impedance, and I'm not sure whether that's 600 ohms or whatever, because remember, 600 ohm output from the secondary of the transformer is going through that thing there. That's the filter. And it then goes off and goes into the recorder itself. But I don't know what the output impedance is, and I don't know whether it will affect the response much if it's unloaded. So I decided to load it, and I've got these two Croc connectors connected to the output. And what I'm going to do is I'm going to use a 10K pot This is a multi-tone pot, which is pretty good. I'm going to put it on the variable setting. And this is the same thing as putting a load on it. In other words, as if it's seeing the input of the recorder. And I'm going to match, well, first of all, I want to know what the output impedance of that is. And then I can match it. I can load it with the same amount. And the best way to do that is to set, if I touch this, it comes down slightly, as you can see. I've put a 10K load on there. But I don't know what the output impedance is that thing is producing. So the way to do that is to actually just connect this up here, or rather, let me rephrase that. I'm going to set that to a round voltage by increasing the amplitude. Let's call it 4 volts. And this is only true for 1 kilohertz, remember, because I have to find some reference. Okay, so 4 volts at 1 kilohertz, and I'm now going to put this across there. And I'm going to start dropping that resistance till I get 2 volts on here. And what am I doing? There is a condition that when your output impedance is equal to the load, you've got the two perfectly matched. And the result is that the actual voltage that you measure across the load becomes exactly half what you will see if it's unloaded, like that. Unloaded, 4 volts, loaded, 2 volts. Okay? So if I take that off now, and this is a pretty exact pot, and I did start with it on maximum. I don't want to short the output. I know that this thing contains the value, the resistive impedance value of that, what I'm supposed to load that with. So I'm going to measure this resistance now. So our output impedance of that system there is 1.5K, 1.4K rather. I'm going to load it with that. In fact, I might just leave this in there. And then I'm going to try and plot the response curve from 20 hertz to 20 kilohertz and see what we get. Okay, let's do this. I've got the this device is an interface that's going to take the signal from the output. It interfaces to the PC Soundcard because I want to see the response on the Visual Analyzer software. I did a little project on this a while back. I'll link it above. We'll put it on 1 times, switch it on. Okay, here we go. Got a 1 kilohertz sine wave on there. I'm going to put a sweep on from 20 hertz to 20 kilohertz so we can see the sweep going through there. I'm going to hit peak hold. We'll let it sweep through a few times so we can get a solid line for the curve. And that should do it. Okay, that should do it. There we go. So we've got, this thing's fairly flat up to about 1 kilohertz. Then it starts curving up gently to about, what is that, 6.8 kilohertz. Comes down again. And you back down, well, about 15 kilohertz, back to that level over there. So now I'm going to switch that on again. And what I'm going to do is I'm going to flick it from 7.5 inches per second to 15 inches per second. And we'll hit hold again and see what happens. Oh, we can definitely see a change there. Yep, most definitely. Okay, here we go. Flat, 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 flat. It starts a bit later. Instead of starting at about 1 kilohertz, it starts sort of climbing at about 2 kilohertz. And then it peaks at 12.5 and then starts coming down up to 20 kilohertz. So what we've got here is really the difference in the kind of filtering you need between the one setting, speed setting, and the other. All right, what does this tell us? The faster tape speed allows you to pump it in with a bit more high frequencies. It gives you more hi-fi, so I presume that's why you do that. Now this has got to do with the response of the actual tape head itself, which we might see when we get the transport into my grubby little hands, which I've been promised, and I'll be able to put the two together and we'll be able to test it. All right, good. That's pretty clear. I knew it would be something different, but I didn't know it would be like this. Now we have the answer. And all good things must come to an end. Well, not really, but in this case, yes, this project is done. There is something else I want to do. Not sure exactly when I'll be able to do that, and that is to grab the transport, connect it to this, check what's necessary in the transport. I've spoken to the owner. He wants me to do that as well. So who knows, maybe in the very near future we'll be able to see this thing actually operating and taping, recording and playing back and all that other good stuff. So yeah, we've got this thing working. It's looking good. It's in pretty good cosmetic condition. It was really, just needed a bit of cleanup. But that's it for now. And yeah, I want to thank you for tagging along on this project, keeping me company. I hope you've enjoyed that. If you have, do please click like or dislike, whatever. Interaction is always good for the YouTube algorithm, as the saying goes. And if you want to support the channel directly, you can do so on Patreon. Links are at the end of the video or below in the description. Once again, thanks for watching. Bye for now and stay safe.